What does computational thinking mean? Computational thinking is a system composed of many components which they interact with each other, and therefore it's a complex system. And as for all complex systems, when we try to model them after oral or written language, we do risk losing some essentials. So instead of me just jumping in and trying to give you a definition of computational thinking, I want to walk you over some examples about what does not fit this system. And then we're going to look at some history and see understanding where we were and where we are today. And based on that, I will give you my definition of computational thinking. Then we can look at some examples of how to use computational thinking in our day-to-day life and job. Take a look at this bus in this example. I took this from a series called Brain Games. In this research, they actually showed this bus to adults and children and asked them if this bus was going to move forward, which direction would it go? I'll give you a second to think. So when they asked this from small kids who take bus to school every day, the correct answer, it's important to know that, the correct answer came to them almost automatically. They look at this, they did not see a door to enter the bus, therefore the door must be on the other side. And the side that you're seeing right now is the side that the driver sits. So the answer is, it really depends. Do you live in US or in UK? So it depends on where you are and the culture and the rules, the answer could be different, right? So these examples like this, that the answer really depends on some common sense or culture, they're not really computational thinking. You're not running that many algorithms. You might overanalyze, but we're not running any algorithms to understand and have the correct answer to this. Another example that doesn't fit computational thinking is art, or things that has to do with subjective opinion. This picture was sold for $450 million. And I would love to understand why, but I will never have anything to prove that actually this picture worth that much. Obviously it did to somebody, right? So anything that has to do with subjective opinion, you cannot say that's a computational thinking. Money itself, I would argue, is very subjective. Another great example, and this is my favorite, is impulsive behavior. When you're in a mosh pit, you're not thinking computationally. So unless you're a physics student or someone who knows about collective behavior, this is what Jesse Silverberg did. He actually loved attending mosh pits, and once he was like far away and looked at the mosh pit and this collective behavior from distance, and he had just learned that concept. So it hit him that actually this is a collective behavior. He went home and started building this model to simulate what's happening. And I think this shows you that it's very different being in the mosh pit than model the patterns of movement of mosh pit. So some have described computational thinking as thinking like a programmer. I want you to think about that a little bit. If computational thinking is thinking like a programmer and you hire enough full stack developers, then you should have no problem solving all the problems, anything that needs that computational thinking, correct? It just happened that sometimes we hire the full stack overflow developers. And these are developers who, they have an error in their code and they take that error, Google it, they probably land on some Stack Overflow page, copy the first answer they see without really understanding why that error was there or why this solution was suggested. They copy paste that in their code, they run again, they run into another different error, and they just repeat that behavior without really taking time to understand what is actually going on. A little bit about me. I'm Sarah Aslanifar. I'm co-founder of Tested Minds and interim CTO at Car Advice. For the past 15 years, I was really keen into learning programming languages and tools, and of course, love to solve problems. I was fascinated. I went from DOS to C++ to Python to Clojure, Java, and then suddenly I started to think, what's really the purpose behind learning all of these languages and all of these tools? And the moment of truth for me was when we had kids. My husband and I had kids. Suddenly I had to think, how would I prepare my kids to grow up and be successful, not knowing what's ahead of us in 20 years, especially in such a fast-speed world that we live in. How would I teach my kids to be successful? My bet was that I can teach them how to learn and how to adapt and how to differentiate between subjective and objective opinions and how to analyze the messages that they see in the media or on the computer, on the news, and find the truth. So I want them, especially that's important, especially these days that most schools are moving towards like remote schools. So kids are spending a lot more time on iPads and the computer. And we need to really teach them that the computer is not just for games or just do school homework. They can actually use these machines to think with. So that brings us to this quote from John Culkin that he says, "Life imitates art. We shape our tools and thereafter they shape us." This is a huge claim. So what my takeaway from this is that there is information in the artifact that we develop and we produce as culture. And that information changes us and changes our culture over time. So this, again, it's a very big claim, but there's some supporting evidence to this. For that reason, let's go back and look at the history of Homo sapiens. Most researchers dated Homo sapiens somewhere around 200,000 years ago in Africa. For all that time, but small fraction, our ancestors relied on oral cultures to pass knowledge from one generation to another. And when you have when you rely only on oral cultures, the message always changes from speaker to a listener. And when the message changes, there is no objective truth. And that's why these times are called prehistoric, because we don't know much about them. We can't even call our ancestors illiterate because there was no form of writing or reading even invented. Walter Ong spent most of his professional career, exploring the impact of cultures moving from orality to literacy and the impact on their culture and their education. If I were to show you this slide, with few tools, and I just give you answer, but with few tools and a log, and ask you which item does not belong, which one do you pick? I bet most of you picked the log. The log does not belong, because we have a concept of abstractions. But in oral cultures, they don't have that abstractions like a set of tools. When they look at this picture, they see a couple tools that they can use to cut the logs, but not so much to do with the hammer. So they actually choose the hammer. The hammer does not belong. In oral cultures, concepts are used in a way that it minimizes abstractions, focusing to the greatest extent possible on objects and the situations that are known by the speaker. And this example shows you that the writing actually restructures your brain. So that telephone game and the oral culture continued for about 150,000 years. And that's why we call that prehistory. Again, we don't have a lot of artifacts to really prove and understand our ancestors, the way they lived, the things they knew. We don't see any evidence in writing until about 5,000 to 6,000 years ago. And the earliest alphabet appears right about 1,000 years after that. And even though at that time a form of writing and reading existed, that didn't mean that everybody saw that it's necessary for them to pick up and learn that. In fact, only a few people, scribes and religious leaders, politicians, saw it necessary to learn how to read and write. And for the rest of the commoners, that was just confined. They weren't allowed to read and write, because the reading and writing was information, and information was a form of power. So things started to change for craft literacy when printing revolution begins in about mid-15th century, when Johannes Gutenberg invented printing press in Germany. And that, in order of magnitude, it made it easier for us to capture knowledge, for the knowledge to be captured, mass-produced, and be preserved over time and space. So for once now, this changed what was printed, by whom, what was the read, and what was the thought. To put that in perspective, when we look at some of the data, in about 1400, the population was about 400 million. And by 1800, our population just about doubled, a little bit more. What happened to printed books? We went from zero, or at least close to zero, to 1 billion in the 18th century. And the effect that had on cultures, and this data is for Europe, you can see that we went from less than 20% of people knowing how to read and write to, in some cases, to about above 80%. And it's very important to know that these new readers in this growing population are working with new ideas. And this was our transition from the Middle Ages. So here, Marshall McLuhan is talking about the effect of media, and media, especially writing, on Greek culture. And in the same way, printing made literature possible. It didn't just merely encode that. And it's also important to note that what was printed wasn't just the production of the same idea of oral and craft literacy period. And also, we're not talking about books just like Shakespeare. We're talking about books like this, the trigonometric function written in 1619. This is data. That this table of content, this book, was extremely error-prone, if at all possible, to be written by scribes and religious leaders. But printing press made this happen, and people like Matthias Berneger, who was a child growing up in Protestant Reformation after printing press, he was able to write his ideas down and produce this book, which then later on went to be used by astronomers and navigators and building architects. So let's come forward a little bit. This is a more recent example. In 1940s, people like Betty Stafford on the left, she was recruited from PhD programs during World War II to work for earlier versions of NASA. And these people were praised for doing more in one morning than an aerospace engineer could have finished in one day. And here you see that she is actually understanding or jotting ideas about conversion of log 10 of a number to a natural log. Of course, she has some tools, she has calculators, but most of these thoughts and these ideas was in her head. So World War II also funded a massive amount of R&D into human and mechanical computing to solve problems for automated fire control. And also they start investing a lot of money into electronic computers. So ENIAC is a great example. The original or the first computers, also women, who were the programmers, not only they had to have a really good understanding of the problem, they had to come up with a good solution for it. And they had to have a great knowledge of the actual computers to be able to rewire and change these cables in order to test their ideas and program. So it's important that this was electronic and this was you could reprogram them, but reprogramming was not as fast. So what they really needed was a good abstraction to let them really focus on the problem at hand rather than understanding the details and the implementation of the computer. And speaking of abstractions, when you have too little abstractions, it loses the power. And when you have too much abstractions, that really makes you distracted from the problem at hand. In this case, it's literally a leaky abstraction. So the decision on what amount of abstraction is right, it really depends on your job and what you need to accomplish. So in about 1945, the von Neumann architecture gives us stored programs. At this point, we don't need to worry about the details and implementations and the actual mechanic of the computer. We can focus on the problem, and those problems, those ideas become code, and that code becomes data. Now we have an object that we can think with and we can use to express our ideas, to test our ideas. So here's another example. In this example, this is from Betty, who is probably understanding or modeling a downwash and writing her ideas. You can see that she has a drawing. And on the other side, this is from Dr. Lorena Barb, that she's learning or understanding computational fluid dynamics. And when you look at them side by side, you can see what Betty had to go through to get her idea tested versus Dr. Lorena Barba. She could just open Jupyter Notebook, write few lines of program, run the code, see actually visually see how the code implements, and tweak as much as she wanted. So that feedback was very fast. So just to give you an idea, what happened is that these objects to think with are as important in media as alphabet and printing press were to our ancestors. We just came from orality to literacy to computability. We are among the first generation in our history that is able to interactively explore our ideas and our concept on a machine that executes those instructions with no subjective judgment and no permission required. And this makes our ideas falsifiable and tangible. We have an object that we can use to think with, and even better, we can share those results almost instantly with anybody, anywhere in the world. So your ability to understand those abstractions we talked about, your tools or programming languages, it really depends on your job function and your goals. In some cases, you might just be a power user. You just want to copy paste some ideas and use some library without really knowing what or needing to know what's going on behind it. And that's okay. And are you okay with that? In other cases, you might actually open every single library or every single tool that you're using with and have a great and deep understanding of those libraries or tools. In that case, I would say you're probably a professor at the university in a computer science department. Are you okay with that? So what's important to note here is that you don't stop when you have a perfect model. You stop when you have an imperfect model that you understand. But the more abstractions we understand, the larger our toolbox is and the better we can think. So knowing a programming language, the things and tools that you use in day-to-day life, it just makes you faster and makes you more productive to focus on the problem you're actually trying to solve. All models are wrong, but some are useful. So if I were to define computational thinking, this is my definition, that the computational thinking is an iterative system of generative reasoning in which people build models of subjects in a notation capable of being executed by a computer objectively and automatically with observable and falsifiable outputs. I'll give you a second to just digest that. So it's really easy to take that for granted, to take that capability for granted. But as we saw through the history, that shows you that in our entire civilization, we are among, this has been just doable in less than a century, and we are right there. As Brian Merrick says, an example would be handy just about now. So let's look at even in DevOps world. One example for this is, let's imagine you want to create a VPC and subnets by going through the UI, AWS, EC2 console, and click through to build what you need. What part of that process is executable by a computer? What if you make a mistake? How do you know that you made a mistake? And how are you planning to transfer that knowledge to a person who might have to support that after you? So by turning this manual process in something that's precise, infrastructure as a code, it helps capturing these steps and the knowledge to create and recreate these environments and in everything that you're planning on doing. A good example of this is Terraform. Terraform is declarative, so you don't really have to understand every detailed implementation behind Terraform. You can use it as a tool to just tell it where to implement that plan and what's your end goal. So now if the Terraform is the what, I would say ADRs or architecture decision record is the why behind it. So it's always great that you have use code and that's executable by the computer, but augment that with some documentations. ADR consists of status, context, and decisions and consequences of all of those decisions. What debates happened between you and your team? Was there any pros and cons? What was other options? Were you thinking about Terraform versus CloudFormation? What was the reason that you finally decided to use one over another? Joseph Blake recently described an experience like this in his team at Spotify, that the why of the ADR combined with the what and how of infrastructure as code makes a great start for knowledge transfer and onboarding. So a big takeaway from this talk is that you have an object that you can think with. You can think with, you can explore. You don't have to wait weeks and days even sometimes. You can build tests, you can write your tests, you can build simulators. So just like the map is not the territory, your code is not the computational thinking. Your tests, simulations, documentation should help recreating all of those computational thinking that went into the design. And that's all I have. Thank you for your time. We are hiring at Car Advice. I would love to hear from you, whether it's about hiring or any thoughts and comments that you have on computational thinking. Thank you for your time.